Would you like to lose a little bit of weight without doing any exercise or dieting? Would you like to age just a bit more slowly than your friends? Well, you might be surprised to hear the laws of physics can help. The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In the previous episode, we used cutting-edge technology to investigate how gravity changes your weight.
It's gone up.
Your height. I really have shrunk. And even your posture. In this show, with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
Throughout the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work.
Oh, wow.
And in exploring it, I'll be challenged on how I understand this most mysterious force.
Wow, okay, I need to go and write this one down.
And I'll have to tackle the very nature of reality itself. Gravity. What goes up must come down. All of our lives, we abide by its rules. It dominates our every action. But there's one select group of humans who know what it's like to live free of gravity.
2, 1, 0. Liftoff.
Everybody's used to gravity. We're used to the oppression of it. Gravity is the ultimate oppressor. It grinds us under its heel 24/7 with no release until you're in space. And then suddenly you're free from gravity. You're weightless in orbit.
Canadian astronaut Chris Hadfield spent 5 months on board the International Space Station.
You can pull your knees up to your chest and just tumble. Or if you take a wet cloth and you get it dripping wet, and everybody on Earth knows what'll happen when you wring it out. All the water will fall inevitably. If you do that in weightlessness, the water stays there, and it actually, because of the surface tension, starts crawling up your arms. It's a little bit mesmerizing and hypnotic to be in weightlessness. If you're weightless, you don't need a bed, you don't need a mattress, you don't need a pillow. Your body is floating completely suspended like magic. Movement becomes effortless. You can push off with one finger and fly and tumble. You don't need to hold yourself where you are with muscle. You can just, with a delicate fingertip pressure, you can stay where you are.
Okay, separation confirmed, timer is on.
Backing away at a rate of just a little over 1/10 of a meter per second.
Re-entering gravity is a punishing experience.
Okay.
To come back to Earth is violent. It can be 5 times the force of gravity or 8 times the force of gravity, crushing you down into the floor of the ship for quite a long time. Then, of course, you hit the ground and tumble and roll to a stop, and now you're the victim of your past. You're the victim of your decision-making, lying there, trying to shake your head and get used to being in gravity again. I remarked at the time that I had forgotten that my lips have weight, and my tongue has weight. You don't think about it. But if you try and talk articulately standing on your head, you'll notice that you have to sort of control your lips and your tongue a little differently just because gravity's pushing them the other way. And it's the same sort of thing, raising your arm, holding your head up, turning your head when everything wants to tumble, just keeping your balance, all of those things. It's a little bit like relearning to walk again, like an infant.
Gravity shapes our bodies and molds our planet. Nothing happens on Earth without its power and influence. Sir Isaac Newton explained so many of its effects using one simple equation. And in the centuries that followed, his laws of physics led to breakthrough after breakthrough, spurring on the Industrial Revolution. But in the first decade of the 20th century, the next genius in our story challenged the very foundations of our understanding of gravity. A young German scientist called Albert Einstein was churning something over in his mind. He thought that something in Newton's laws didn't quite add up.
Imagine I'm the sun, and this tennis ball is the Earth in orbit around me. Newton's laws can describe very precisely the path the Earth takes around the sun in terms of the mutual gravitational attraction between the two bodies. But what Newton can't explain is what connects them. In reality, of course, there is no invisible string between the Earth and the sun holding the two together. There's just empty space, a complete void. And yet, according to Newton, the Earth and sun pull on each other instantaneously across a vast distance. How can gravity act in this way when there's nothing to connect it or transmit it?
After years puzzling over this, Einstein had a blinding flash of inspiration. Just like Galileo and his ramp, or Newton with his apple, Einstein's breakthrough came because he was thinking about one simple action. What happens when something falls? To explain, I'm visiting this 400-foot-high tower in Northampton, built to safety test lifts.
One day in 1907, Einstein had what he called the happiest thought of his life. What if I was standing in a stationary lift, completely isolated from the outside world, not feeling anything apart from the pull of gravity on my feet? What if then the lift cable breaks and I start falling? What are the forces that I will feel as I'm plummeting to the ground? Well, I'm not going to try that. Fortunately, there's another way to test this without me having to plunge down a lift shaft. Sorry to disappoint you. This little device here that I've strapped to this plastic toy is an industrial accelerometer, so it measures acceleration. Now, I've got it connected to my laptop, and it's showing a measurement of 1g. Now, that's the downward acceleration due to the pull of Earth's gravity. So basically, it works just like a gravity meter. But what happens if I were to drop it? Presumably, it'll carry on measuring 1g because it's falling in Earth's gravity. Okay, well, let's try that and see. So you can see here along this line at the bottom, that's when I was holding it still, and it's measuring an acceleration of 1g. These oscillations here is when I stood up and there's a bit of disturbance, but this spike along here is the moment I released it. And this short duration along here is the time it was falling. And you see, while it was falling, it was registering an acceleration of 0. Now, if you think about it, this is really odd. The accelerometer is accelerating downwards, it's plummeting in the full grip of Earth's gravity, and yet it's measuring no acceleration at all. It's as though gravity has completely disappeared.
Einstein's insight was that when something falls, it no longer feels the pull of gravity. In fact, falling is like floating in empty space. This is the essence of Einstein's happy thought, and what we now call his principle of equivalence. Einstein's point is that when the man in the lift falls, he doesn't just feel weightless, he is weightless.
Einstein said the man feels no force pulling on him because there is no force pulling on him. Gravity doesn't act on him, it acts on the space and time around him, what we now call the geometry of space-time.
This was a radical redefinition. Einstein says forget the idea of gravity as a force acting mysteriously between two objects. Now we have to think of it as the shape of space-time changing.
You see, Newton saw space and time as independent, fixed, and immutable. That three-dimensional space is the stage in which things happen. But time is separate. It ticks by at the same rate everywhere in the universe. According to Newton, an object would travel through space in a straight line unless acted upon by a force like gravity that will cause it to deviate from that path. But Einstein said that space and time aren't fixed and immutable. They're interconnected, meshed together in what is known as space-time. And he said that space-time can be warped, that matter curves space and time around it.
So after Einstein, we no longer see gravity as an invisible string pulling objects together. Instead, a body like the Earth warps the structure of space and time around it. And an object in orbit follows a path which is as straight as possible through that space-time. It's a fundamental part of Einstein's vision of reality. Space and time can't be disentangled. You can't talk about space separately from time. So matter warps time as well as space. It's known as gravitational time dilation, and it's possibly the strangest of all of Einstein's discoveries.
I've got two identical clocks here. Now, because the clock lower down is closer to the center of the Earth, it feels ever so slightly a stronger gravitational pull than the clock higher up. Einstein's theory says that the lower clock will tick by at a slightly slower rate than the higher clock. Basically, gravity slows time down.
It's an extraordinary conception of reality that Einstein describes. Space is being curved and time is being distorted. So why can't we perceive this in our everyday lives? Einstein had a rather nice way of explaining it.
Most of us have had the experience as children of trying to work out what our parents do for a living. Well, imagine your father is Albert Einstein. When he was about 12 years old, young Edward Einstein asked his father why he was so famous, what he'd discovered. Well, this put Einstein Sr. on the spot, but he came up with a beautifully simple analogy.
Einstein told his son, when a blind beetle crawls over the surface of a curved branch, it doesn't notice that the track it has covered is curved. I was lucky enough to notice what the beetle didn't notice.
This is what Einstein meant. The beetle is free to move in any direction on the branch. It can move forwards, backwards, left and right, but it has no concept of a direction up off the branch. It's as though, for the beetle, the universe is missing the third dimension. The beetle may think it's moving in a straight line along the branch, but we can see that the surface it's walking on is itself curving and twisted.
Einstein's point was that what we see as the twists and curves of the branch feel to the beetle like forces pushing and pulling it. Okay, so consider this rather strange example. Imagine we have two beetles perched on this pumpkin, and for whatever reason, they want to walk up towards the top. Now, if they start at the equator, pointing due north, as they walk, they will begin by moving parallel to each other. That means their paths should never meet. But as they get closer to the top, their paths get closer together. Now, if they're clever beetles, they might try and figure out what's going on, and they could imagine that there's some mysterious force that's pulling them closer together. But for us, from our perspective, we can see there is no such force. All they're doing is following straight paths over a curved surface. Just as the beetles have no sense that the surface of the branch is curved, we completely fail to perceive the bizarre ways that gravity shapes the reality we live in. Einstein's problem was proving that he was right. After years more thought, he realized that there was a way. By looking far out into the solar system. Incredibly, here in the grounds of Hurstmonceau Castle is housed one of the original telescopes that were used to prove Einstein was correct.
In 1915, when Einstein developed his general theory of relativity, it was just that. It was a theory. It had no proof. In fact, many people found it completely outlandish. But then just 4 years later, in 1919, this telescope, and allow me to geek out a bit here, and I'll give it its correct name. This is the 13-inch astrographic refractor. This telescope proved that Einstein was in fact right, that gravity does curve space itself.
Since then, observation after observation have confirmed that matter curves space and slows down time. So the simple question of why things fall the way they do has led us deeper and deeper into the very nature of space and time itself. Gravitational science shows us how galaxies, stars, and planets form. By measuring gravity, we've discovered the existence of dark matter, that 80% of the mass of our universe is invisible, and we don't know what it's made of. And we've detected exotic objects with extreme gravity, like neutron stars, which have more mass than our sun, yet are only 20 kilometers across. But it's another mysterious aspect of Einstein's universe that I want to explore in my next gravity project. Here at the University of Surrey, some colleagues and I have been working on it for months.
What we're doing is devising a nationwide citizen science project. We're developing a smartphone app that uses the GPS contained on your phone to explore one of the strangest properties of gravity, how it affects the rate at which we age.
I formulated the equations myself, and a small team of computer scientists and software developers is using them to devise the app. Einstein discovered that as gravity changes, so does the rate that time ticks. This means the strength of gravity you feel affects how quickly or slowly you age. The aim of my app is to demonstrate this effect. It works by using a phone's GPS data to estimate your local gravity. And it also calculates the average speed at which you move, because this too affects the rate at which you age. It then uses the equations I've written, which are based on Einstein's theory of relativity, to calculate overall how fast or slowly you're aging. Once the app is ready, I tweet about it. Thousands of people download it, and we start to gather results from across the country. Some people send me videos giving me their results. how fast they're aging compared with how time ticks out in space in zero gravity.
Over the past day, I have aged less by about 172 microseconds.
I have aged less by 10.02 milliseconds.
So since downloading the app, I have aged less by 1.14 milliseconds.
Since opening Time Warp, I have aged less by 2.6 milliseconds.
Our aim is to use their results to build up a map of how time flows because of gravity. My smartphone project provides just one insight into the space and time which Einstein's theories describe. Gravity and its strange ways have given us astonishing insights into the dark secrets of our universe. Perhaps the weirdest objects in the universe are black holes, collapsed stars whose gravity is so strong that not even light can escape their grip. Now, for the first time ever, their effects have been felt on Earth, and they've been detected through the medium of gravity itself. It's a story that has revolutionized the study of modern cosmology. 1.3 billion years ago, in a galaxy far, far away, two black holes swirled around each other, drew closer and closer together until they finally collided with incredible violence. In that final fraction of a second, at the precise moment that they merged, a disturbance was created that sent ripples out through the universe. Gravitational waves are a key prediction of Einstein's theory. Matter doesn't just curve space-time, it can cause waves, ripples which expand outwards, exactly like a stone dropped in water. This particular wave was unimaginably large. The energy released was greater than all the light being given out by all the stars in the universe. The wave rippled through space at the speed of light. In 1.3 billion years, it covered a distance of over 10 billion trillion kilometers. Until, on the morning of the 14th of September, 2015, it arrived here. The streets and cafes of New Orleans, in fact, everything in America and on Earth, expanded and contracted very, very slightly as the wave passed through. No one noticed, as by the time it arrived here, the distortion was phenomenally tiny. Except that one science laboratory did notice. And I'm going to see it. 1,000 scientists across the world are collaborating on it. It's the culmination of over 50 years of effort and is one of the most sophisticated experiments ever devised by humanity. So I'm pretty excited to see it. It's a rather unusual setting. Here I am in the middle of rural Louisiana, about an hour's drive outside New Orleans. I don't expect to find such a multi-million-dollar cutting-edge research facility as this. And yet, this is the place where recently one of the most important scientific discoveries in human history was made. This is LIGO. The Laser Interferometer Gravitational Wave Observatory is an enormous construction shaped like an L, with a sophisticated laser system bouncing up and down the two arms.
So we're standing on top of one of LIGO's two arms. This is the first LIGO arm. And in that tube, there's a laser beam that we bounce back and forth between a mirror in the end station and a mirror in this building. And the other bit goes that way, 4 kilometers, perpendicular to the arm we first saw.
This is the L shape.
It's a big L on the ground. So the light bounces back and forth in that arm and bounces back and forth in this arm. And what we actually measure with LIGO is the length of this arm as measured by the light between the 2 mirrors, and the length of that arm as measured by the light between 2 mirrors. And then the laser interferometry measures the difference between those 2 arm lengths.
So as the gravitational wave passed through, the lasers picked it up. They detected that LIGO's 2 arms changed in length to a very, very tiny degree.
The signal that we saw was just a few thousandth of the size of the atomic nucleus. It's the biggest the signal ever got.
So far, far smaller than the size of a single atom.
Oh, much, much smaller, yeah, that would.
And you need something this huge to pick that up.
That's right. And so this is one of the biggest source of energy in the universe, one of the biggest events you'd ever measure, and we just barely saw it.
The LIGO scientists turned the gravitational waves into sound waves. So what you're about to hear is, in a very real sense, the sound of 2 black holes colliding.
It was the first observation of any kind of pairs of stellar mass black holes. Stellar mass means, you know, several or a bunch of suns in weight. And so we learned that they exist. We learned that there are enough of them that occasionally they run into each other and coalesce. And we also learned by comparing the waveform we observed with general relativity calculations that general relativity is, as far as we know, dead on right.
The long concrete bunker to my left houses the beamline, one of the LIGO's laser arms. The detail and the effort that's gone into isolating the beam from the outside environment reminds me very much of Cavendish's famous experiment. He too had to worry about isolating his experiment from external disturbances. Only, of course, LIGO takes things to a far, far greater degree.
Inside the arm is one of the largest and purest vacuums in the world. Atmospheric pressure in there has been reduced to 1/1,000,000th of the pressure outside. The mirrors inside are so reflective that they only absorb 1 in 3 million photons. And at the end of my little trip lies a British success story.
Well, I made it all the way to the end of one of the LIGO arms. To be honest, it took me a bit longer than I thought, especially in that thing. But housed inside this building is one of the reflecting mirrors that bounces the laser beam all the way back down the 4-kilometer arm to the main control center. And the technology that went into developing these mirrors is quite remarkable. It was developed in the UK at the University of Glasgow.
This is what the mirror looks like. Its surface is extraordinarily smooth. No bump bigger than a few billionths of a meter high. Equally amazing are these. Fused silica fibers, a few times the thickness of a human hair. Designed by the University of Glasgow in conjunction with scientists from other British universities. They isolate the mirror completely, so it hangs perfectly still. You could say that in there is the quietest place on Earth. Despite this, outside events do sometimes interfere with the work here, as I witnessed for myself.
I've wandered into the control room here at LIGO because I'm told something kicked off a few hours ago, and they're all very busy. The image that's flickering up there is not meant to be like that. Essentially, what they've picked up is a seismic disturbance, an earthquake. Now, that's not an earthquake down the road. It started on the other side of the planet, in Japan. So it just gives us a sense of the tremendous challenges faced by LIGO and the team here, and the level of sensitivity needed, that an earthquake on the other side of the Earth can disrupt their measurements and have to reset everything all over again.
One of the scientists involved in developing this extraordinary place put it quite succinctly. Once we were blind, but now we can see.
Throughout the entire history of astronomy, we've studied gravity and how it affects matter in the universe and how it warps space-time, but only by looking at the light that enters our telescopes. Now, for the first time, we can study the universe in a different way. The discovery of gravitational waves means we can see objects that cause extreme warping of space-time and its effect on gravity directly. This essentially opens up a new era in astronomy. It gives us a new way of looking out at the universe.
Professor Sheila Rowan was one of the scientists who spearheaded the British effort for LIGO. For her and her colleagues, gravitational wave detection is just in its infancy. New instruments, even more sensitive than LIGO, are now being developed.
There's so much that we don't understand about the universe that we live in, and this has suddenly given us a new tool, a new way to probe the dark processes in the universe. Because every time we make the observatories more sensitive, we can sense gravitational wave signals from further away, from farther out in the universe, from further back in cosmic history. Things like supermassive black holes spiraling in to collide, small black holes orbiting round supermassive black holes, tracing out the dents in space-time of those supermassive objects. A long-term goal is to probe back further towards what we think of as the Big Bang, the earliest moments that we understand of the universe as we know it.
If you think about it, time and time again in the history of science, unlocking the mysteries of gravity have led to a deeper understanding of the universe. Galileo and his ramp, Newton and his apple, Einstein and the falling man in the lift. Each of these characters challenged the scientific consensus of the day. And even today, understanding the true nature of gravity remains one of the biggest challenges in science.
Which brings me back to the smartphone app. And it's at this point that our story, for me at least, takes a completely unexpected turn. Unfortunately, it's all gone a bit pear-shaped.
Okay, so here's what's happened. A couple of months ago, we launched the app, and it was all going really well. Thousands of people downloaded it and have been sending us their results. We've been collecting the data to create this nationwide map to show how time flows at different rates for different people around the country. Unfortunately, I've just realized there's a big problem. You see, I was going over the scientific literature, and I came across this subtle point about relativity, which basically made me sit bolt upright. There was this horrible, dawning realization that I've made a mistake in the equations that get fed into the app.
So what this means is, all the results we've been gathering are wrong.
The issue lies in the strange and subtle effects of Einstein's theories of relativity, and it's fundamental to the way time flows across the surface of the globe. Now, what if I use my smartphone app where I live here on the south coast of England, and then go and spend a few days down near the equator, say here on the west coast of Africa?
Now, we know from the road trip that gravity is weaker by the equator. So that means time ticks faster there.
But there's another important factor we have to take into account: movement. You see, when I'm here near the equator, I'm moving more quickly than I was back in Britain because of the rotation of the Earth.
Einstein says movement slows down time, so clocks will tick slower at the equator.
This is where the error crept in. You see, I had taken into account these two effects, but I'd missed a crucial point. They cancel each other out exactly. In fact, the Earth bulges out exactly the right amount for its rotational speed to make sure they cancel out. So all clocks on the surface of the Earth at sea level tick at exactly the same rate.
So now I'm having to go right back to square one and completely rewrite the equations for the app. And to test if it's working, I'm going to use it over the course of a normal working week.
This is where I live. This is Portsmouth, which means I'm very close to sea level. And this is how I start most mornings, catching the train to work.
The app records my speed as I'm on the train and calculates how this slows down my personal clock.
But I think the train journey should have slowed my time down by a few trillionths of a second.
I'm heading for the BBC's headquarters in central London, and gravity should be a bit weaker here.
I'm a few meters above sea level, I guess, here, and so there'll be a speed up of my time because of altitude.
The app compares the way my time flows with a stationary clock at sea level. So what's my result? On an average day, my movement makes me age slower by 1/3 of a nanosecond. That's 1/3 of a billionth of a second. But the weaker gravity I'm in means I age faster. Overall, 1/2 a nanosecond faster.
Approximately do about 1,000 miles a week, sometimes more, depending on the number of meetings I have.
He lives close to sea level at the iconic John O'Groats.
I run a tourism business and I started about 50 years ago. So when people come here, they can actually physically speak to someone who's been born in John O'Groats. And if they ask questions, I can tell them all sorts of useless information because I'm full of useless information.
So our final results show that if you want to age more slowly, try to live near sea level, like Walter. Or there is another way to do it. Get a job on the International Space Station. Its 17,000-mile-an-hour orbit will give you a boost.
We did the math for the astronauts. Every month, you are about 1 millisecond younger. So, 1,000th of a second. So after 6 months, you are that much younger than people on Earth. So I'm younger than I should be. I hope I look it.
Of course, for us on Earth, time dilation is so utterly minuscule, a few billionths of a second between us, you might think it's too frivolous to even bother about. And yet, in the long and difficult process of designing the app, I've come to an extraordinary conclusion. The different ways that time flows may not be some quirky byproduct of gravity. It may actually be gravity. It may be the cause of gravity, the reason why objects fall.
One of the colleagues I've been consulting is Kip Thorne. He's one of the world's leading theoretical physicists and a driving force behind the creation of LIGO. While I was going back over some of the basic physics behind the app, I came across an intriguing idea of his. It's a very interesting and different way of describing gravity.
This is what Kip says. Everything likes to live where it'll age the most slowly, and gravity pulls it there. Kip's based at Caltech in California and is one of the most respected theoretical physicists in the world.
Firstly, Kip, a serious thank you for helping out with the debacle over the app.
Well, I sympathize. I've made so many errors in my own over the years that I am totally sympathetic.
One of the things that struck me thinking about this is something you wrote, Kip. You said, everything likes to live where it'll age the most slowly, and gravity pulls it there. Was this a way of explaining something that you felt was a neat explanation, or is there something deeply profound about that?
I think there is something deeply profound in some sense, but it's a lovely description of Einstein's first major insight about gravity in 1912. He realized that gravity that we feel on Earth is due to a slowing of time on Earth.
So time comes before gravity in that sense. You know, on the Earth's surface, time runs more slowly, and that accounts for why gravity wants to keep us there.
Well, I think in a very deep sense this is true. Objects want to fall, that the flow of time, or the rate of flow of time, is the thing that produces the gravity. It is the thing that is ultimately responsible for the fall.
So somehow it's in the nature of all objects to move towards a region where time runs slower. Kip's formulation works anywhere in the universe where the gravitational field is such as on Earth.
The difference in the rate of flow of time is tiny. At high altitude and on the surface of the Earth, the difference in the rate of flow of time is 1 second in 100 years. That's not very much, but that is enough. That is precisely the right amount to produce the gravitational pull that we feel and produce the accelerations we're talking about.
Wow, okay, I need to go and write this one down.
So my investigation deep into the weird ways of gravity has finally left me face to face with one of the greatest mysteries in all of physics: the nature of time itself. It sounds like such a simple question. Why does the apple fall? And yet hundreds of years of scientific inquiry investigating this single action have led us to completely redefine the way we think about the very nature of space and time. And now I've been presented with this extraordinary proposition that somehow, in some profound way, the apple falls because it's seeking out the place where time runs the slowest. So does gravity dictate the flow of time, or does time itself define gravity? Could this hint to fundamental new laws of physics as yet undiscovered? I think I'm going to have to think about this a bit more.